Hello everyone, my name is Hoàng Ngơ. I'm going to present a work on edge of information in prioritized random access. This is a joint work with Giuseppe Durisi and Alexander Amat. We are working at Chalmers University of Technology. In our work, we consider a status update system in which there are a number of devices, which can be sensors and health monitoring devices. They run on battery and they want to transmit status updates to a common receiver through a random access channel. The updates are timestamps to keep track of their generation time, and the goal is to deliver these updates not only successfully, but also timely to keep them fresh. So we want to guarantee some constraints on the edge of information, which is the offset between the current time and the timestamp in the last received update. On top of that, we also want to minimize the power, and here we use the number of transmitted packets to determine the power. Furthermore, we assume that the users are divided into different classes with different requirements in terms of freshness. In total, we have U devices. They belong to K classes. The fraction of users in class K is gamma K. Time is divided into slots. And the probability that a user in class K has a new update in a slot is mu K, independent of the other users. We consider irregular repetition slotted ALOHA as a communication protocol. Time is divided into frames of length m. Each user can have a new update multiple times in a frame, but only the latest update will be transmitted in randomly chosen slots of the next frame. For example, here the class 1 users transmit 3 times the packets. Class 2 users transmit 2 times the packets. We consider a collision channel. The receiver uses successive interference cancellation to decode. It first finds a slot with only a single packet transmitted, decodes the packet, and then removes the replicas. And it continues like that until no more single packet slots can be found. We define for class K a degree distribution and write it in polynomial form. So the coefficients corresponding to power L is the probability that the user in class K choose L slots to transmit the packet. We also define a channel load, which is the average number of active users in class K normalized by the frame size. The packet loss rate of class K is denoted by pk, and the total average number of packets per slot is denoted by phi, and is computed as the sum of the channel loss of each class multiplied by the average number of packets transmitted by a user in that class. The edge of information of user I at slot n is n minus the timestamp of the last received update from user I. If we plot the edge value versus the slot index, we see that it has this sawtooth shape. So the edge value increases monotonically within the frame and is reset at the end of the frame only if there is a new packet successfully decoded. Within a frame, the big edge is at the end of the frame and is given by the edge at the beginning of the frame added with the frame size. The edge violation probability is defined as the limiting probability that the edge at the end of a generic frame exceeds a certain threshold. Later on, we'll see that the edge process is algorithmic Markovian, so this limit exists. To keep the updates fresh, we want to satisfy some edge requirements in the sense that the edge violation probability for certain threshold theta k is smaller than a small value epsilon k for all users in class K. Now we analyze further the edge process. It is a direct extension of the single class case reported by Munari. First, the probability that the edge of a class K user is reset is given by the product of the probability that the user transmits a packet and the probability that the packet is successfully decoded. Another important quantity is the initial offset between the generation of a new packet and the end of the corresponding frame. It has this probability mass function. Now to keep track of the edge process, we can keep track of the process denoted by omega j, which is the edge in the beginning of a frame j minus the lower bound m plus 1 of the edge. This process is algorithmic Markovian, and it has this steady state distribution. Here w is an edge value. It is decomposed into beta w frames and a remainder alpha w. This probability is basically given by the probability that the edge is first reset to a value alpha w plus 1, which is the initial offset, and then the edge is not reset after beta w frames. With that, we can compute the edge violation probability as the tail probability of this steady-state distribution, and we obtain this closed form expression. Now we are ready to formulate the optimization problem. We want to minimize the average number of packets transmitted per slot, subject to some edge requirements, and we minimize it over the update probability, mu, and the degree distribution lambda of each class. Here there are some interesting trade-offs. First, if we choose a low update probability, then a new update is generated after a long time, and the information in the last update can be stale. On the other hand, if we choose a high update probability, then a user transmits many packets, the channel can be congested, which leads to update failure. The second trade-off is about the choice of the degree distributions. If we choose a degree distribution with high degrees, then we can reduce the packet loss rate, but we increase the number of packets transmitted. On the other hand, if we choose a distribution with low degrees, then we reduce the number of transmitted packets, but we increase the packet loss rate. To see this trade-off, let's consider an example with 4,000 users, frame length 100, two classes, 20% of the users are in class 1 and 80% are in class 2. We fix the same update probability as mu for both classes. The edge threshold for first class is 60,000 and for second class is 30,000. We want to satisfy edge violation probability of 10 to the minus 3 for class 1 and 10 to the minus 1 for class 2. So here we plot the edge violation probability versus the number of packets per slot for some distribution. First, with the distribution with only degree 1, so each packet is transmitted only one time, we see directly the first trade-off. If the number of packets per slot is low or mu is low, then the edge violation probability is high because the update is too sporadic. On the other hand, if the number of packets per slot is high or mu is high, then the edge violation probability is also high because of the channel congestion. We also see that we do not satisfy the requirements of both classes with degree 1. So let's use a degree 2 for both classes. Now we can satisfy the requirements for both classes with about 1 packet per slot. What about degree 3 for both classes? In this case, we can still satisfy the requirements for both classes, but we need to use a higher number of packets per slot. On the other hand, we can reduce further the edge violation probability, and we can satisfy more stringent requirements. For example, 10 to the minus 4 for class 1 with about 1.95 packets per slot. Next, when we optimize the system, we'll need to compute the packet loss rate for many different degree distributions. It would be more efficient if we have accurate approximation of the packet loss rate, which is easy to compute. The packet loss rate of a user in class K is given by the weighted sum of the packet loss rate of a general degree L user, where the weight is the probability that a user in class K has degree L. This BL is determined by the average degree distribution. The packet loss rate is characterized by two regions, the waterfall region and the arrow flow region. In the asymptotic regime, when the frame size is large, we can evaluate PL using density evolution. It is given by the limit of this quantity eta I to the power L when I goes to infinity. This eta I can be easily computed in an iterative manner. We call this approximation BLDE, and with that, the packet loss rate has this shape. So it drops at a certain channel load, which is called the decoding threshold G star. In the waterfall region, PL can be approximated using the finite length scaling of the frame error rate of the equivalent LDPC code. In this way, BL is approximated by this formula, where PG to 1 is the packet loss rate when the channel load is 1 computed with density evolution. Q is the Gaussian Q function. G star is the decoding threshold that we have mentioned. And alpha and beta are scaling parameters which are computed for each degree distribution. We call this approximation BL waterfall. In the arrow flow region, we can approximate PL following this work. So the idea is that in this region, the decoding failure are mostly caused by a harmful structure in the decoding graph, which is called stopping set. So to count the number of unresolved degree L users, we count the number of stopping sets and the number of degree L users intersect. We call this approximation BL error flow. With that, we consider two approximations of the bucket loss rate. The first one is the sum of the error flow and the waterfall approximations. The second one is asymptotic value computed with density evolution. Here we plot the bucket loss rate and the corresponding edge violation probability versus the number of buckets per slot for some distributions. First, for the distribution with only degree 3, the first approximation works very well. The second approximation is over-optimistic in terms of the edge violation probability when the number of buckets per slot is moderate. However, when we have only degree 2, then the first approximation is very loose in the waterfall region. The reason is that the final length scaling is not guaranteed to hold for degrees 1 and 2. On the other hand, the second approximation works quite well. If we have only degree 1, then the first approximation simply doesn't work at all. The second approximation works very well. From these observations and some further experiments, we propose the following heuristic. If there is degree 1, then we approximate PL by the value from density evolution. If there is no degree 1, then we approximate PL using density evolution for L equals to 2, and by the sum of the error flow and the waterfall approximations for L larger than 2. Now let's consider an example. We consider the same system as before with 4,000 users, frame length 100, two classes, 20% of the users are in class 1 and 80% are in class 2. We fix the same update probability as mu for both classes and restrict to degree distributions of degrees 1, 2, and 3. We minimize the average number of transmitted packets per slot over the update probability and the degree distributions of the two classes subject to some edge requirements. So the edge threshold for the first class is 60,000 and for the second class is 30,000. We are going to use the bucket loss rate from the simulation and from the approximation that we proposed, and we are going to compare them. To solve this minimization, we use the nadir-mid simplex algorithm. So next, we are going to take some values of the epsilon 1 and epsilon 2 and show our optimization result. First, consider epsilon 1 to be 10 to the minus 2 and epsilon 2 10 to the minus 1. Here we plot the edge violation probability versus the number of buckets per slot for a reference distribution with only degree 1 and for the optimized distribution with either simulated or approximate bucket loss rate. We see that the results from simulated and approximate bucket loss rate are similar, but they have almost no gain. And actually, the optimized distribution has mostly degree 1. So this confirms that for my requirement, degree 1 would be enough. However, if we make the requirements more stringent, say 2 times 10 to the minus 4 for the first class, then degree 1 is not enough. We need to use higher degree. So let's use degree 2 for the class 1. In this case, we can satisfy the requirements for both classes. However, we can do better than that. We can optimize the distribution. Here, again, the optimized distribution with either simulated or approximate bucket loss rate are similar, and they bring 21% improvement. Now let's consider even more stringent requirements. Say 10 to the minus 4 for the first class and 10 to the minus 2 for the second class. Then if we use regular distribution, we need to use degree 3 for both classes. But we can do better than that. We can again optimize the distribution. With a simulation-based optimization, we achieve 12% improvement. The result with approximate bucket loss rate is slightly worse than that, but is still significantly better than the reference. Finally, let me conclude the talk and give some takeaway messages. In our work, we have considered the problem of multi-class status update. We studied the edge power trade-off. We optimize the update probability and the degree distribution of each class to minimize the number of transmitted packets. We propose a heuristic bucket loss rate approximation. Our optimization results suggest that we need to use irregular degree distributions. And from further experiments, we see that degrees 1, 2, and 3 are sufficient for the parameters that we tested. Thank you for your attention, and we are looking forward to your question.